Okay, so this is where we start our course, Chapter 7. Our book covers algebra and trigonometry, but we're only interested in the trigonometry, which begins in Chapter 7. 7.1, we're going to be talking about angles, which is sort of the most basic object that we look at in trigonometry. This section is going to cover a lot of things. Much of it is terminology and kind of getting used to the way that we look at angles in this course. So to begin with, some geometric definitions, starting with a ray. If you've been through geometry, this is something you would have looked at before. A ray is a point and the set of all points extending in one direction from that point. Basically, you think of it as a line which doesn't go forever in both directions. It has a starting point in a sense, and then it goes forever in the direction of a line away from that point. So we call that a ray. The definition of an angle is interesting. Now, the idea of what an angle is something that we're probably all familiar with. It's a familiar concept, but trying to define it mathematically might be kind of a difficult thing if you're not used to how things are defined formally in math. So the way that we define an angle is we define it to be two rays, two of these, that share a common endpoint. That endpoint is called a vertex. So here's an example of an angle. You can see there's the common endpoint here. It's labeled vertex. It's point E, and it extends, or the two rays extend in different directions in this case. Together they form this thing called an angle. Now, there's different naming conventions that we use for angles. In this case, if I have a point on each ray as well as the vertex, I can name my angle according to those points. So this is being called angle DEF, and we think of that as going, sort of tracing out the angle in the order that we see these written, DEF. You can call this angle FED as well. It's just tracing it in the opposite direction. So that's one naming convention. If you've been through geometry, that's one you've seen before. Okay. We oftentimes need to represent angles using some kind of symbol, kind of like an algebra, using a letter of the alphabet for a variable, representing some real number, for example. In trigonometry, it's very common to use Greek letters for the naming of angles, and these are really the most common Greek letters. You don't have to know the whole Greek alphabet, but the ones that are going to be most important: theta, phi, alpha, beta, and gamma. Theta being the one that we're going to be seeing the most frequently. So you'll get used to those Greek letters. Alpha, beta, and gamma are going to be really important when we get to chapter 10. Now, one thing that we also commonly do with angles is we imply some sort of orientation or direction to that angle. And what I mean by that is an angle being defined as two different rays. If we think of one ray as sort of a starting point, and the other ray as rotating away from that first ray. So one way you can think of this is this ray here, which I'm calling the initial side. You can think of that as a doorway. And the terminal side, you can think of that as the actual door. And we're looking at this door from top down. So as the door opens, the terminal side moves away from the initial side. Notice that that implies a sort of direction, because there's this starting position and then this ending position, this initial side and this terminal side. Those terms are going to become important. Okay. Now, another thing that we do a lot of in trigonometry is we superimpose coordinates over angles. And that leads to this definition of what we call standard position for an angle. So when we talk about an angle in standard position, what we mean is that its vertex is located at the origin in the Cartesian plane, the xy axes. The initial side of the angle will always be positioned to overlap with the positive x-axis, and the terminal side is just wherever it would be for that angle. But this is what we call standard position. And in standard position, that terminal side can be thought of as having moved away from the initial side in a counterclockwise rotation. That's what you're seeing here. This is counterclockwise, indicated by where that arrow is pointing. Or you can think about the terminal side as having been rotated clockwise from that initial side. When we get to the measurement of angles using degrees and radians, we're going to see that the choice of counterclockwise versus clockwise is what makes the difference between angles being measured with positive numbers or negative numbers, but we'll get to that soon. Okay, so far it's just terminology, kind of understanding what we're talking about when we talk about angles, initial sides, terminal sides, all that stuff. Okay, let's get into the measurement of angles. So most of you, if not all of you, should be familiar with measuring angles in degrees. Even people who haven't been in a math class in decades know, for the most part, what it means for what it means to take a 360-degree turn or something like that. It's a pretty familiar concept. Something worth mentioning that might be interesting to some people is why we use 360 degrees at all. It might seem like an odd choice. Why not 100 degrees for a whole circle? Where's the 360 coming from? And in fact, it's been used for so long that we don't actually know its origins with certainty, but there's some theories as to why we use 360 degrees. This is not going to be something I test you on. It's just a little tidbit if you're interested. But if you think about it, the number 360 is actually very, very close to the number 365. It's just off by 5, and 365 is the number of days in a year. So it seems likely that there's some relationship between the measurement of an angle and the use of degrees to measure an angle and the calendar year. In fact, a lot of ancient cultures, Mayans in particular, but other ancient cultures as well, the Babylonians, they would use celestial mechanics and things like the calendar for mathematical purposes. It kind of formed the basis of their number system some of those times. And the number 360 is kind of a natural one to see come up. But it's 360, not 365. Why aren't we using 365 degrees? And the reason for rounding that down to 360 is because 360 has a lot of factors. It's a highly, highly divisible number. And one thing that we do very often with angles is we cut them up into pieces. We look at, not a full circle, but a fraction of a circle. A number with a lot of factors is convenient when you're taking fractional values or dividing that number up, because dividing it by 3, 4, 5, 12, whatever, it oftentimes will give you a whole number. So the number 360 is convenient for those calculation types of purposes. But one thing we're going to see as we kind of do a little bit with degrees is that we're actually going to kind of discard it. Even though, I shouldn't say discard it, we're going to kind of move towards a different system for measuring angles, something that's more conducive for calculus and the stuff that comes after this course. So anyways, it's kind of an unnecessary history lesson, but there you go. So the way that we think of a degree is if you were to measure an angle by taking the initial side and then the terminal side, having it rotate in a complete circle and coming back to the initial side overlapping again, thinking of that full circle as an angle. We call the measure of that angle 360 degrees. And so you can oftentimes you say there's 360 degrees in a full circle. Another way of thinking of that is what does it mean to have 1 degree? Well, that would naturally mean that we're looking at 1/360th of a full circle, which would be very small, hard for me to draw in this little picture down here. Now, again, because 360 is easy to chop up into fractions, it makes it easy to work with other angles that are smaller than a full circle. So we'll get to that in just a moment, but to kind of build on what I had mentioned earlier, counterclockwise versus clockwise. So when we measure an angle that's in standard position like this, if we think of the terminal side as having been rotated counterclockwise away from the initial side to measure that angle, then whatever value we're using, whether it's degrees, radians, or some other way of measuring an angle, we'll make that a positive number. If an angle is measured clockwise from its initial side, then we are going to use negative numbers to represent those angles. And we'll look at some examples of that in a moment. A little bit more terminology to talk about, though. So again, when we're putting these angles in standard position like this, we're using the coordinate plane. And with that comes some of the conveniences of the coordinate plane. So for one thing, the two axes cut the plane up into these four quadrants, which we label 1, 2, 3, 4 using Roman numerals. I just realized I was pointing off the page there for a moment, but you can see here the first, second, third, and fourth quadrant. So we'll talk in a little bit about what it means for an angle to be in a quadrant, but before we do that, I want to talk about a special set of angles that we call quadrantal angles, and really all those are angles that are in standard position, and their terminal side coincides with one of the axes, whether the positive x, positive y, negative x, or negative y axis. And so that gives us four special angles. A 0-degree angle, which we interpret to be an angle where the initial side and terminal side are the same. There's no opening of that door, if you will. A 90-degree angle, which is like a perfect corner. A 180-degree angle, which makes basically a straight line. Notice that that terminal side is on the negative x-axis here. That makes it a quadrantal angle. And a 270-degree angle, that's three 90-degree angles, making 3/4 of a circle. Okay, and then 360 degrees would bring us kind of right back to this starting point where the terminal and initial side coincide again. So those are what we call quadrantal angles. Okay, now when angles are not a quadrantal angle, then the terminal side will be in one of the quadrants. You can think of the axes as like the border line between quadrants. So if an angle is not quadrantal, then one of its terminal side is going to point into one of those. And in those cases, we identify the angle with the location of its terminal side. So I can say, for example, a 45-degree angle is in quadrant 1, because if you think of this 90-degree angle as sort of surrounding quadrant 1, 45 degrees is going to point right through the middle. The terminal side would be in quadrant 1. And we're going to use that convention a lot. Wherever the terminal side lies, that's where we're going to say that the angle lives. So a lot of terminology, a lot of definitions and basic concepts here, but we haven't really done any examples yet. So let's look at some examples. For these four angles here, we want to sketch the angle in standard position, which means we want to put it in the coordinate plane. And then we want to determine which quadrants they lie in. So starting with this 135-degree angle, I'm going to sketch out my coordinate plane, and I'm not going to worry too much about it being super accurate for this. We just kind of want to get used to the idea. So again, remember, when you're working in standard position, the angle is always going to have its initial side coinciding with the x-axis. Now 135 degrees, we like to use these quadrantal angles as sort of like stepping stones into whatever degree or whatever angle we're working with. So what I mean by that, 135 degrees is equal to 90 degrees plus 45 degrees. And you don't need to write this out every time you're sketching an angle. It just helps you visualize it a little bit more. So as I go from the positive x-axis to my 135-degree angle, 90 degrees, this first value, is going to take me up to the positive y-axis. And then 45 degrees is half of 90, so that's going to take me halfway into quadrant 2. Okay? So that's where the 135-degree angle is. Now to make sure I'm labeling things, I'm going to use this little curve to denote that angle, and I'm going to also write in that it's 135 degrees. Now notice the terminal side for this angle is pointing into quadrant 2. So I'm going to notate that by writing Q and then the Roman numeral 2. That's saying that this angle is in quadrant 2. Okay? Let's go ahead and do this next one. Notice we have a negative angle in this case, negative 60 degrees. Okay, so I want to determine where that's going to be. Now remember, this first angle, I rotated counterclockwise from my positive x-axis to get to that terminal side. And that's because this was in a positive angle here. With a negative angle, we're going to move clockwise as opposed to counterclockwise. So that's really all the negative is being used for. Beyond that, I just think of it as a 60-degree angle. Now 60 is less than 90, so it's not even going to take me to the next axis. It's just going to take me 2/3 of the way there. 60 is 2/3 of 90. So I'm going to just kind of do a rough estimate as to where that is. It's not perfectly accurate, and that's going to be fine for this example. This would be my negative 60-degree angle. Okay. Now, notice that's pointing down into the fourth quadrant, so I would say that this belongs to quadrant 4. Okay, Roman numeral 4. Negative 390 degrees. Now, this one has a couple of oddities with it. First of all, it's negative, so we know that that means we're looking at a clockwise rotation. But not only that, it's more, or it's less than negative 360. So essentially what that amounts to is more than a full circle measured clockwise. And I mentioned that up here. I didn't talk about that yet. We can think of angles being that are greater than 360 degrees or less than negative 360 degrees as just being more than one full circular rotation. So if I were to try and sketch this out, it's going to help me to break down the angle into easier to manage chunks. So again, negative 390 degrees. Just looking at it, I know that that's more than a full circle because it's less than negative 360. So I'm going to write it as negative 360 plus whatever else I need to add to that to get to negative 390. That would be negative 30 degrees. Okay, so this negative 360 degrees is like going from my x-axis clockwise all the way around until I get back to my x-axis again. And then the negative 30 degrees takes me an additional 30 degrees clockwise. So that's going to end up looking kind of like this, okay? And the way I'm going to notate that with my little curve is I'm going to make one full rotation and then kind of spiral outward until I get to that terminal side. That's what a negative 390 degree angle would look like, okay? One more. I've got to squeeze this in here. 810 degrees. That's a very large angle, or as far as the degree measure, but it's positive, so we know that it means we're moving counterclockwise from our positive x-axis. Now, let's go like this. So think about this for a second. 360 degrees would be one full rotation. An additional 360 degrees, that's 360 plus 360, that's 720 degrees. So 720 degrees is 2 full circles. Let me see if I could break down 810 into 720 plus a little bit more. 810 is equal to 720 plus 90 degrees. Okay, so this basically means that in order to sketch an 810 degree angle, I have to think of going counterclockwise 2 full rotations, because that's 720 degrees, and then an additional 90, taking me to the positive y-axis. So I'm going to sketch that this way. 1, 2 full rotations, maybe you kind of spiral out, and then stops right there. That's an 810 degree angle. And notice this one, I forgot to write the quadrant in the last one, I just realized. So this one also is in quadrant 4. And notice this one is a quadrantal angle. It's not in a quadrant because it landed, the terminal side landed on the positive y-axis, which is a border between 2 quadrants. So it's not in a quadrant, it's a quadrantal angle. I'm just going to write quadrantal for that one. Okay, so that's all the time that I have for this first video. We'll go ahead and pick up where we left off in the next one.